Have you ever felt like there's this secret language, a mathematical code that's describing everything all around us? I mean, from the arc of a perfect basketball shot to the crazy twists of a roller coaster, there's a hidden set of rules that governs all these curves. Well, today, we're going to decode a huge part of that language.
All right, let's just jump right in with a question. I want you to picture a soaring suspension bridge. Then think about one of those up and down kind of chaotic stock market charts. And then a stunningly realistic 3D movie. They seem totally different, right? I mean, what could they possibly have in common? Well, what if I told you they all share the exact same mathematical backbone?
Believe it or not, the answer is polynomials. Yep, this one, powerful concept from algebra, is like the invisible architect behind all of them. It's the tool that lets us model, predict, and even create all the complex curves we see out there in the world.
And I'm not just talking about a few random examples either. Think about it. Engineers? They're using polynomials to figure out how a bridge will hold up under all that weight. People in finance? They're modeling market trends with them. Physics? You can perfectly chart the path of a thrown ball. And those amazing 3D movies? Animators use polynomials to create those smooth, lifelike curves on characters. They are quite literally everywhere.
Okay, so we get it. They're super important. But what is a polynomial really? Let's break it down and get into the fundamentals, kind of like decoding the DNA of these amazing functions.
So at its heart, a polynomial is just a math expression. It's got variables, like x, and those variables are raised to whole number exponents, and they're multiplied by some numbers. But here's the key, the one thing you absolutely have to remember visually. The graph of a polynomial is always smooth and continuous. No breaks, no gaps, no sharp, jagged corners. Ever.
And you can really see what I mean here. On one side, you've got these nice, elegant, flowing curves. You could literally trace the whole thing without ever lifting your pen off the paper. That is a polynomial. But then look at the other side. You see those sharp corners, those sudden breaks? Nope, those are not polynomials. That smooth, unbroken flow is the dead giveaway.
Okay, so to really get a handle on what a polynomial is going to look like, you only need two little pieces of information right up front. First, its degree, that's just the highest exponent you see. And second, its leading coefficient, that's the number attached to that first term. Seriously, these two clues are like a crystal ball for predicting the graph's behavior.
And this chart shows you exactly why that's so powerful. This is called the leading term test. And what it means is, just by knowing if the degree is even or odd, and if that first number is positive or negative, you can instantly know what the ends of the graph are doing. We call it the end behavior. It's an incredible shortcut to figuring out the big picture shape before you do any other work.
All right, so now we've got a handle on the overall shape. Let's dig into the most important part of our investigation, this quest for zeros. Now, zeros, or roots, or x-intercepts, they all mean the same thing, are just the spots where the graph physically crosses or touches that main horizontal line, the x-axis.
And this brings us to one of the most powerful ideas in all of algebra. It's called the fundamental theorem of algebra, and it's basically a guarantee. It promises us that whatever the degree of the polynomial is, say degree 5, then it will have exactly 5 roots. Not 4, not 6. Exactly 5. But there's a catch. We might not be able to see all of them on the graph.
And that's because roots come in two flavors, real and complex. Real roots are the easy ones. They're the ones you can physically see, where the graph hits the x-axis. But complex roots, they're kind of like hidden solutions. They don't show up on the graph, but they have to exist to make that fundamental theorem true. So you might have a third-degree polynomial that only crosses the axis once, but you're guaranteed that it has 2 other roots, and they must be a pair of these hidden complex roots.
So the big question is, how do we find all of these roots, the visible ones and the hidden ones? Well, for that, we need a toolkit. I want you to think of yourself as a math detective, and these next 4 tools are going to be what you use to crack the case.
And here's our 4-step method, our game plan. First, we list all the suspects using something called the rational root theorem. Step 2, we find clues to narrow down that list with Descartes' rule of signs. Step 3, we confirm a root. We prove one of our suspects is the real deal with the factor theorem. And finally, step 4, we break down the polynomial with synthetic division. Let's take a quick look at how each tool works.
Okay, tool number 1, the rational root theorem. This is how we create our list of suspects. All you do is look at the numbers at the very end and very beginning of the polynomial.
This theorem gives you a way to create a list of all the possible rational roots. Now, it's not going to tell you which ones are the real roots, but it takes an infinite number of possibilities and boils it down to a nice, manageable list.
Next up, Tool 2, Descartes' Rule of Signs. This one is like a criminal profiler. You just look through the polynomial and count how many times the sign flips from positive to negative, or negative to positive. That simple count tells you the maximum number of positive roots to look for and the maximum number of negative ones. It's an amazing clue that tells us where to focus our investigation.
Then we have the factor theorem. This is our confirmation tool, and it's awesome because it's so easy. You just take one of your suspects from the list, plug that number into the polynomial, and do the math. If you get 0 as the answer, boom, you've done it. You have just confirmed that number is a root. It's that simple.
And once you've confirmed a root, you bring in the heavy hitter, synthetic division. This is just a super fast, streamlined way to divide your polynomial by the root you just found, and the goal is to break it down. So if you start with, say, a 5th-degree polynomial and divide out one root, you're left with a much simpler 4th-degree one to solve. You just keep doing that until the whole thing is cracked.
All right, we've got the theory down, we've got our detective's toolkit. Now for the really fun part, the payoff. Let's put all these clues together and see how we can sketch a graph completely from scratch, just using what we've learned.
So here's our polynomial for this example. Now at first glance, it might look a little intimidating, but trust me, with the tools we have, we can figure out exactly what this thing is going to look like. First things first, let's collect our clues. What's the degree? Well, if you were to multiply this whole thing out, you'd have an x squared term and an x cubed term, which gives you x to the 5th power. So our degree is 5, that's an odd number, and the leading coefficient is going to be positive. So think back to our chart. Odd degree, positive coefficient. That means the graph starts down on the left and ends up on the right. And hey, the zeros are handed to us on a silver platter. We've got x equals 2 and x equals -1. But now we have to talk about something called multiplicity. This is so cool. Look at the 0 at x equals 2. See how its factor is squared? That exponent, 2, is an even number. Whenever the multiplicity is even, the graph just comes up, touches the axis, and bounces right off. Now look at the 0 at x equals -1. Its factor is cubed. The exponent, 3, is an odd number. And whenever the multiplicity is odd, the graph goes straight on through. It crosses the axis. And now we just put it all together. It's like telling a story. We know it has to start low on the left, right? So it comes up, it hits our first 0 at -1. The multiplicity there was odd, so it crosses right through. Then it's got to turn around at some point, and it comes back down to our second 0 at 2. The multiplicity here was even, so what does it do? It just touches the axis and bounces off, heading up and to the right, which perfectly matches the end behavior we predicted from the start. See how all the clues fit?
And there you have it. We went from what looked like a complicated jumble of symbols to a curve that is completely predictable. We didn't just guess and check points, no. We used logic and our toolkit to understand the story of the function. We've totally cracked the code.
And you know, that's the real magic of math, isn't it? It gives us this incredible language to describe the world, to describe the universe. So next time you're out and you see a gracefully arching bridge or maybe a satellite dish pointed at the sky, you'll know the secret language behind it. So my question to you is, now that you can read the secret language of curves, what other patterns in the world around you are you going to start to decode?